From the moment humanity first sparked a fire, to the roaring engines that powered the steam trains of the Industrial Revolution, the mastery of heat transfer has been the driving force behind our technological evolution. Today, that same fundamental science is the bedrock of modern thermal management. But when we take these systems into the aerospace sector, the stakes change entirely. Up in the sky, heat exchangers must survive a series of extreme operating conditions and unforgiving constraints on weight and pressure. In order to tackle these challenges, my research applies a multi-level modeling workflow from 1D analytical coding to 3D CFD across 3 specific case studies. The first one is a benchmark study of a shell and tube heat exchanger. For this, I developed a 1D numerical model in Python utilizing the epsilon ATU method. This allowed me to validate my code against analytical correlations and yielded some clear results. The model confirmed the thermodynamic superiority of counterflow arrangements over parallel flow, and more importantly, it successfully quantified the severe degradation of performance due to surface fouling. The results demonstrated a drastic drop in thermal effectiveness, plummeting from approximately 55% in a clean state down to just 12% in full scenarios. This highlights exactly why aerospace designs require advanced, fouling-resistant materials. The second case study focuses on air-cooled horizontally opposed reciprocating engines. The main challenge here is cooling the cylinders effectively without adding excessive weight or aerodynamic drag. In order to evaluate this, I'm performing 3D CFD simulations to analyze the thermal performance of different fin configurations. The goal is to map the temperature distribution and strictly optimize the fin geometry, finding the perfect balance that maximizes heat rejection while keeping the engine's mass and aerodynamic penalty to an absolute minimum. My third case study explores an intercooled recuperative aerobic engine proposed by MTU Aero Engines. This technology has been modeled in SolidWorks according to the specified dimensions. As we know, traditional turbofans operate on the standard break-on cycle. The intercooled recuperated aero engine improves this cycle with 2 key additions. First, intercooling, which reduces the work required by the compressor by cooling the air between compressing stages. And second, recuperation, which captures waste heat from the exhaust nozzle and drives it back to preheat the combustion chamber, saving a significant amount of fuel. In order to simulate this advanced cycle accurately, I used GasTurb software. By feeding it the exact specifications of the GA1976B engine, I extracted precise temperatures and pressures across the compressor, combustor, turbine, and nozzle. In order to obtain the desired results, I am performing 3D CFD simulations in ANSYS Fluent using a conjugate heat transfer or CHT approach. In simple terms, CHT allows me to simultaneously calculate the heat conducting through the walls and the heat convecting into the surrounding airflow.